Hello everybody, this is Greg Wagner from CIS 250 at Pima Community College, and I want to go over today's lecture going over floating point numbers, also considered like fractions, or also sometimes called decimal numbers or fractional numbers. And so basically I kind of want to quickly review from what we covered in the first week of class, which way the decimal numbers are recorded. So say if we want to cover factor a number. So say we're going to factor the number 256. We break down that number by the place. So remember we have the 0th position, 1st position, 2nd position, which is going to line up to the exponents. And so we have, so this is the 2nd position, so it's going to be, and it's base 10. And so we're going to have the base number here. So it's going to be 4 times 10 to the second. It's going to be 400. 5 times 10 to the first is going to be 50. And then 6 times 10 to the 0th position, or the 1's position, is going to be 6. So 456. And then again, for binary, so again, this is the 0th position, 1st position, 2nd position, and it's base 2. So it's 2 times 2 to the second, 0 times 2 to the 1, 1 times 2 to the 0. We can use the same idea for representing numbers in the floating point positions, or the fractal positions. So in this case we have 0.1456, and so since this is going to be, here's the 0th position, here's negative 1st position, negative 2nd position, apologize for my writing, negative 3rd position. Again, this is base 10. So we have base 10 going to here, negative 1 position. It's going to be 4 times negative 10 to the 1, so this position here. 5 times negative 10 to the 2 is going to be this position here, and 6 times negative 3 is going to be this position. So this should be 0.1, 0.1. So 1 to the negative 0.2, 0 times 2 to the negative 2. And these values would be, so negative 1 is going to be 1/2. So that's 2 to the negative 1. 2 to the negative 2 is going to be 1/8. And if there was a value here, it would be 1/4. So this value is going to be 0.5 times 0.6. And so you basically, you can use these binary numbers to kind of approximate what the fractal numbers are going to be. And so, say we want to represent the number 31 in binary, just kind of as a review from what we would do before. So just as for part of the review, so the numbers are going to be, so how would we make this number into binary? So we can do kind of I'll do the tree method for this one. What I want to do is represent the number 31. And so we want to do this in binary. If you kind of remember how we do this, the number 2 here, and so divide by 2, and so we're going to have 15 with the remainder of 1. Divide the number by 2 again. This is supposed to be a 15, not a 25. And so we're going to get 1, and the number is going to be 7. I have to manage my space well here. Divide by 2, so it's going to be, we put the remainder here, so it's going to be 1, and then 3, divide by 2 again, we're going to get 1, and 1. So 31 should be 1, 1, 1, 1, 1, 1. So this should be 16, or 15 plus 16 is 31. So this would be 1, 1, 1, 1, from base 10 to base 2. And so you can kind of still do the same representation with these numbers. So basically you have 2 to the values. So what you can do is 2 to the negative 1 would be 0.5, 2 to the negative 2 would be 0.25, 2 to the negative 3 would be 0.125. This is equivalent to 1/2. So you have the values here: 1/2, 1/4, 1/8, 1/16, sorry about my writing, 32nd, and 1/64. And so you notice how these values grow by multiples of 2. So you see the base representation here. In base 2, we have 0.1 is going to be 1/10, which is equal to 0.5. 0.01 is 1/4. 0.011 is going to be 1/8, and 1 is 16th. And so how are you going to actually convert these numbers? Well, basically you can combine these two techniques where you have the first front of the number and the back of the number to do the calculations. So in this case, what we do is we normally will calculate the binary of the front of the number and then calculate the binary of the back, or factor it for calculation of the values. So generally what you want to do is you want to calculate the front number first and then calculate the next number back. And I'll give an example here. So the question is, how do you convert a number from decimal to binary? So the integer part, the integer part is going to be the front part. You do that just as you normally would. So remember from the first week of class where we did the number conversions, you do the front part that way. For the floating point part, it's basically there's two techniques. One is you memorize all the negative numbers of powers of 2, and then subtract the biggest number you can. So kind of like what you did for one of the techniques, and then you keep on going till the number is 0. But basically, the thing is, for integer numbers, you can represent a number using binary digits. However, for the fractal portion, sometimes you'll get basically irrational numbers. So you basically want to represent the number as far as you can. And so, say for example, I'm going to do the number 23.75. So first off, I'm going to calculate the 23 portion, and so it's going to represent by this number. And the 0.25, I'm basically going to find, okay, the biggest number I have here is 0.5, subtract that, and do that number to get 0.75. And so your number is going to be a 1, 1 here. So this will be represented as 0.111.11. So how would you do 20.625? So first off, you want to do the 20 portion. So we get 20, so that's going to equal to 16 will be the first portion. So that's 1 followed by 4 digits, and then a 4. So I know we kind of did this in my head already, but 20 is going to be represented as this, going from base 10 to base 2. So how about the number 0.265? So 0.625 is equal to, well, I'm going to find the largest number that fits into the spot. So it's going to be, first number is going to be 0.5. So it's going to be a 1, a 0.1, and the next highest, and so 0.625 minus 0.5 is 0.125. And then, so 125 is smaller than 0.25, and then the next number, largest number, is 1.25. So it's going to be 0.01. And so the total number is going to become, you combine these both, and it becomes 1.100.101. Another method you could do is basically repeat till you get to the number 0. So you multiply the number by 2. If you get a 1, you put a 1 on the on your list and subtract it. Otherwise, you put 0 and repeat. I guess I'll just copy this number here. And so we have 0.25 and 0.01. So I'm going to multiply this by 2. That's going to equal 0.0 or 0.05. And so I'm going to put a 0 for this number down here, 0.0. Multiply this number by 2 again. That's going to equal 1.00. So I put a 1 there. Subtract 1 from this. That equals 0. And then I'm done. How about this other number? So I'll do 0.2 8.25. So I'm going to multiply this number again by 2. This is going to equal 0, 5, 2, 1, 1, 6. I think I did that right. And subtract 1 from that. So the number, the first digit is going to be a 1. And then so I'm going to multiply 625 by 2. So 0, 0, 5, 2, 1. Subtract that number, I'll pull it back up here. So there's another 1 here. So this is going to be 0.25 times 2 equals 0.5. So there's a 0, no 1 in the front here. So I'm going to put a 0 here. And then multiply by 2. It's going to equal 1. So this number is going to be 0.8125, be represented as. However, in some instances, numbers don't break into neat piles. They can go on forever. So, for example, if I do either of these two numbers, I'll pick an easier one. Say if I do the number 0.1, and I use the technique, it's essentially, it's going to go on forever. Following this pattern. So the first number, 0.1, is 0 times 2, another 0 because it's 0.4. It's going to be 0.4 times 2. That's going to be 0.8. And times 2 for this one is going to be 0.16. And eventually it's just going to go in a pattern like this forever. And so a lot of numbers actually don't line up into neat categories. So basically what the number is going to do is just basically repeat it. So I could represent this number as 0. Sorry, this not meant for drawing points. 0.001. 0.0001. For the decimal representation, so you can represent the numbers this way, and then for some numbers, they're going to go into a loop, like the number 0.35 here is just going to go in a loop forever. And so when it comes to actually representing particular amounts of data, so we want to have, so what can we do when we have an infinite loop? Well, basically, you can't always get right numbers, and you only have a limited amount of memory. And so basically what you do is the best approximation. So when you hear about people in computing, when they talk about rounding errors, basically what it is they went into fractal numbers and they just had a pretty close approximation. So you can kind of think about it for like 1/6 or 1/3. The numbers keep on going repeatedly. And so in this case, for 2/3, you get 6666 to 6 to the 7. They just approximate it to 0.666667, or however much space you have in the memory. And so, but given this, how do we represent numbers actually in the computer? So like I said before, you have to represent number. You have to kind of round the numbers because you ran out of. You only have a limited amount of memory. And so what we do is we use the IEEE floating point representation. And basically what that is so if you've heard of a double, it means it's double precision. You basically have 64 bits to encode the number. But single precision, it means you have 32 bits. And then for the actual number, you basically have 3 parts. You're going to be storing off the exponent. Let's see where to have it. I'll back up and go into this. So basically, the parts of the number you're going to be actually storing are the sign, the what we call the significant, or I tend to call it the mantissa, which is the part of the scientific notation number of the number that's after the decimal place, and then the exponent. And I'll show this number is represented in a second. So we have 32. So a float in like Java or C++, it's called a float or single precision number. Basically, you get about 5 or 6 accurate decimal places with this number. And it's essentially 32 binary digits in memory, and then it's a signed value. And then basically, we only use the mantissa because if we're storing the number in binary, and so the binary number, the first number is always going to be 1. And so, for example, I want to store the number 0.01 in decimal. So the number is going to be stored off as on the right here at 001100110011. And so this is basically going to be the basic representation of the number. And then, so 0.001 in binary would be this digit. And so what we want to do is store the number. So what we're going to do is convert it into scientific notation. So scientific notation is going to be, so we want to pick basically the first significant digit, which is the 1 here. And so we're going to convert the number into 1.1100110011 and have the mantissa here. Multiply that number in scientific notation times 2 times. So 2 is going to be, since it's binary, is going to be the base number, and this is going to be negative 110. So essentially, the first significant digits at the 4th position, and so basically this is negative 4. So 0, 1, 2, 3, 4 is this number here. And so the way the numbers actually going to be stored in memory is we store 7 bits. Basically, the number is 32 bits long. So we have 1 bit for the sign, 7 bits for the exponent. So this is 7. 23 for the mantissa or the significant, and then 1 for the sign up front. And so the way we store the number is, well, basically we don't store the first, we drop the first bit, and so we'll store everything after here. We store it in the fractional part. So we have 23 bits values here, 1, 2, 3, 4, 5 to 23. We have 7 bits for the fractal number up here, and since it's a negative number, we'll actually store this as a negative 0.001 and then the sign. And we'll convert this number to 2's complement for memory storage. For doubles, we basically will use another number as well. For doubles, we'll use 64 bits, which expands mantissa and the exponent, but the sign will always stay 1. Well, I hope you guys have a nice week. And I wish I could all be with you guys in person. I miss you guys as a class, and I hope you guys have a nice week. Next week I'll be going over how we actually use floating point numbers in ASM, so I'll be showing you some code next week as well.